Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology, and I'm also with Carleton University Department of Geography and Environmental Studies. In this video, and probably the next few, I'm going to discuss the concept of global dimming and global brightening. So we know that greenhouse gases that are increasing in the atmosphere are trapping heat, and they're increasing the thermal balance, basically, so that the Earth is warming. They're increasing. We have shortwave radiation coming from the sun, goes through the atmosphere, hits the surface of the Earth, heats it up, and that heat is emitted as long-wave radiation or thermal radiation, and that is trapped by greenhouse gases. It excites those molecules. It's selectively absorbed by greenhouse gas molecules, causing them to heat up, causing the atmosphere to heat up, the Earth to heat up, and so on. But also what we have is our industrial civilization is putting up a lot of aerosols into the atmosphere. And these aerosols have a lot of direct effects on the atmosphere, but they also have indirect effects. So I've seen numbers anywhere ranging from 0.5 degrees Celsius to even as high as 4 degrees Celsius for the concept that if we suddenly stop producing all of these aerosol particles, all of this pollution from industrial civilization, that the planet would almost immediately warm up in that range, 0.5 degrees up to 4 degrees. And I'd like to try to throw some light on this matter. And basically, when we talk about aerosols, we can talk about direct effects, which is blocking some radiation, cooling the Earth, or the so-called global dimming. We can also talk about but you also need to talk about the indirect effects. For example, those aerosols or particles in the atmosphere act as cloud condensation nuclei. So therefore, the physical nature of clouds changes. The cloud particles, or the droplets of water that form on these cloud condensation nuclei, if there's a lot of very small nuclei, can make much smaller water droplets, making the clouds brighter, reflecting sunlight, also cooling the Earth. There's also smaller particles in clouds can inhibit rainfall, because rainfall is the building up of the water droplet size over time in clouds. Most clouds don't precipitate out. Most clouds just evaporate eventually, don't produce precipitation. So the lifetime of the clouds is also modified by the aerosols in the atmosphere. So there's all of these different effects. So I want to try to explain some of them to you. It's a very complicated aspect of climate change. It's one of the most difficult areas to model, but we are making headway. There are certain things that we can say about it. So I'm just going to get the light. So when you're researching a topic, it's just one of the easiest places to go to is Wikipedia, get sort of a broad overview. There are, treat it with a bit of a grain of salt. I mean, the accuracy is fairly good, but it's not guaranteed to be, perfect. There will be mistakes in it, but those are usually filtered out over time. So the idea of global dimming is the gradual reduction in the amount of solar radiation, global irradiance at the Earth's surface. So we started systematically measuring radiation on the surface in the 50s, and what we saw was a reduction. It says the order of 4% reduction so this is surface solar radiation from 1960 to 1990. There was an eruption in 91, which caused it to drop even more because of the sulfur dioxide going into the atmosphere. But then there's been a reversal of this trend since about the early 90s. So the idea is that there's an increase in particulates such as sulfate aerosols in the atmosphere, and this causes cooling on the surface. Therefore, it lowers evaporation of water on the surface and reduces it, or interferes with the hydrological cycle. So perhaps has been, attributed to contributing to the drought in the Sahel and previous droughts, can have a cooling effect to partially counteract the effect of greenhouse gases. So that's the idea. So how much does it do it? Okay, so we talk about the increase of aerosol particles in the atmosphere, basically absorbing solar energy, reflecting sunlight back into space from the sun, so that would cool the surface. But these pollutants also become nuclei. So this is a direct effect, blocking the sunlight. The indirect effect is they become nuclei for cloud droplets. The water droplets coalesce around these particles, so if there's more pollution, there's more particulates, you can get clouds consisting of greater number of smaller drops. These can be more highly reflective, but they can also last longer. So there's these effects as well. So let's have a look at some of the issues. I won't talk too much about the history. Just go on to this site and have a look, and you can see some information about the history. But here's the net effect. Now this is a very regional effect because different areas are sources of pollution. So the northern hemisphere, for example, has far more aerosol production from industrial processes than the southern hemisphere. So we would expect to see large effects that are hemispheric based. So here's some numbers from some studies that were done a while ago, and a reduction of terrestrial surface solar radiation on average, 5.3% reduction between 1958 and 85, 2% per decade reduction over 3 decades, 64 to 93, so that would be about 6% total decline, or about 10 watts per square meter, 2.7% decline per decade up to 2000 in another paper, for a total of 20 watts per square meter, so that would be about double this number here roughly, so that would be over 3 or 4 decades, and 4% from 61 to 90, so slightly less, but all in the same sort of ballpark. So we did definitely have a global dimming issue in those particular years. And these measurements were all done over land. So it's not really a global average, it's more like a terrestrial average. So dimming and brightening over the ocean is a bit of an unknown, but it's expected that because of atmospheric circulation patterns, enough of these particles would be carried over the ocean. Generally, in the lower atmosphere, these aerosols are rained out in a week or so. But there's if they travel over the ocean before they're rained out, then that would cause some dimming over the ocean as well. Okay, now, so let's have a look. So one of the ways that this was first noticed is from so-called pan evaporation data. So many farmers, they just have a very cheap, very simple setup where they have a pan of water, they shield it from the wind, perhaps even shield it from direct sunlight, and they measure the decline of the water depth in the pan over time, so they get an idea of how much water is evaporating. So things that will affect that are the surrounding humidity of the air, winds, things like that. Also, so the heating from the sunlight at the surface. So what they found is that from the pan evaporation data was that, and these are easily reproducible low-cost equipment data. There's pans used for agriculture all around the world, long-term data records, half a century or longer. And basically the evaporation was decreasing in those years, the 50s to early 80s, indicating and being indicative of global dimming. Okay, now there's other factors that come into place from aerosols. There's lots of black carbon that also goes into the air. Mostly, it's like soot. Now, black carbon, yes, it blocks the light, but it absorbs the light. It doesn't reflect it. So black carbon in the atmosphere, it causes significant heating on in the atmosphere at altitudes, well above the ground. So it does dim the surface, but it doesn't result in less heating. It actually results in more heating, more global warming, because it's absorbing the energy in the atmosphere. The energy it's not absorbed on the ground and re-emitted up. It's absorbed in the atmosphere, heating the atmosphere, which then heats the earth. Okay, so let's have a look at some of the other stuff. Now, the other thing that's important is the daily temperature variation. Because as we saw from 9/11, when the plane stopped flying for 3 days, there was a great reduction in contrails from the jet aircraft. So these contrails, when they exist, they block some sunlight. So they actually, when there's contrails, the daily temperature maximum is actually lower. And when there's contrails, they reduce the loss of heat from the surface at night. So they trap some of the heat. So the effect of contrails is to lower the daily maximum temperature and raise the daily minimum temperature, reducing the diurnal or daily temperature range. So in the absence of the planes flying from 9/11 over North America, we saw an increase of the daily temperature range by about 1 degree Celsius. So it was actually warmer, hotter temperatures, hotter daily maximum temperatures during the day, and also colder temperatures at night, because that heat wasn't trapped. It could radiate out to space. So it went both ways. It wasn't about a 1 degree Celsius increase in diurnal temperature variation. So we can talk about that too. Now, here's an image of, we can talk about aerosol optical depth, AOD, and how that changes. And here's a record from 1981 to 2005. And what it shows is, you can see the El Chichon volcano in Mexico, which throws all the ash and dust up and blocks, so it increases the optical depth. Light doesn't penetrate through as much, so it cools the surface. For here, Pinatubo was here, but if you look at the trend from early 90s onwards, there's actually a decrease in the aerosol optical depth as clean pollution acts come into place and things like that. There's actually been around the world the decline in the aerosol optical depth. So we had global dimming, 50s to late 80s, and then from 91 on we had global brightening. We're having less aerosol particles in the atmosphere. So a switch from global dimming to global brightening around 1990, and this is key. Okay, and this is attributed to, for example, the Clean Air Act in the U.S. in 1970, strengthening it in 77 and 90. From EPA work. Okay, now you can look at the effect of what happened in terms of actual temperature rise, model temperature rise, greenhouse gases rising up, solar radiation not slightly rising over time here. Ozone, not much change, volcanic, fluctuating, but sulfates are increasing, and sulfates are one of the main things that block light and cause this global dimming. So let's go down here, and so there's the idea. Okay, where are we here? So one of the ideas that this immediately leads to is, if the warming gets out of control, if we increase the planetary albedo by 0.5%, then that would be sufficient to have the effect of CO2 doubling. So if the warming gets out of hand, rises much too rapidly, then we could, if we increase the planetary albedo a very small amount, we can mitigate the effect of CO2 doubling while we gain time to remove CO2 from the atmosphere